Greetings and welcome, friends. How you doing today? We're talking about the root theorem. That's right, the rational root theorem, also known as the rational zero theorem, if you're interested. And this is what it says. What? Lots of stuff. Here it goes. Rational root theorem. It says let f of x equal, and then it gives us some like long polynomial thing. And the important things to gather from this is it's in standard form, and that a sub 0, also read as a naught sometimes, and a sub n. Those are the ones that we're interested in today. A sub 0 is the leading coefficient, and a sub n is the constant term in our polynomial. Those are the ones we're looking at. So that's what we need to know, okay? The rest of it is just basically indicating that it's a polynomial in standard form. So look at those two things. Good to know those. It says represent a polynomial function with integral coefficients. What I mean by integral is they are integers, right? Kind of like whole numbers, but they include the negatives, right? So blam. It says if p over q is a rational number, meaning it's a number that can be written as fraction, right? In simplest form, and is a zero of y equals f of x, all right? So let's say this happens to be one of my x-intercepts, whatever p over q is. It says these two things. Then p is a factor of a sub n, and q is a factor of a sub 0. That's right. So that means the p is a factor from that, and the q is a factor from that, and its ratio happens to be one of our zeros. So essentially what this is going to allow us to do, right, using previous theorems like Descartes, he told us what possible signs, right, whether it's positive, negative, or imaginary, what kinds of zeros and how many of each we had. This is going to narrow it down further, where it's going to tell me all of my possible rational, all right, zeros that I have. Okay, it's going to give me all of the rational ones. Now, it is possible that I could have an x-intercept like the square root of 3, and that would not be in this list that I'm going to derive from these p's and q's. But this will give me a really good place to start instead of guessing and checking from like infinitely many numbers to try to figure out which one of these might be an x-intercept. This is going to narrow down our list quite a bit that we'll be able to work with it from there. Now, it turns out the rational root theorem also has a corollary, referred to as the integral zero theorem. And it says if the coefficients of the function are integers such that a sub 0 equals 1, so if my leading coefficient's 1, and if a sub n is not 0, then any rational zeros of the function must be factors of a sub n. Basically, they're not saying anything that impressive. Basically, if this was a 1, then p over q would have just been the factors of a sub n over 1. And it's like, thanks for the really insightful thing you gave us there, corollary. Right? That's like if I was writing this really huge, like 30-page paper, and then someone came along and was like, oh, you should write your name at the top. I was like, I was going to do that. Like, I'm not going to share credit with you just because you gave me that idea. I was obviously going to do that. Come on, right? So here's an example of a corollary that's not that powerful, but it's true. So mathematicians write things down that are true sometimes. So here we go. Let's do an example of this. Put this to use. Exemple. Find all possible rational zeros. Posible. Rational zeros. Rational zeros. All right. So let's say I've got this function. I don't know. I'll call it f of x. Why not? And it's equal to x cubed minus 5x squared minus 22x plus 56. Okay. All right. So using our previous skills, I know by the fundamental theorem of algebra and its corollary that there's 3 zeros or x-intercepts altogether, right? Good job. I could also use Descartes' rule of signs to analyze this further, but what I want to point out is that p, the p values for my rational zeros, are going to be the possible factors of 56. So that's going to be like plus or minus 1 and plus or minus 56. It's going to be like plus or minus 2. And what goes into 56 twice? Is that 28, I believe? Plus or minus, does 3 go in? No, I don't think so. No, because 5 and 6 add to 11. That doesn't work. But 4 does. 4 goes into 28. 7 times 7 times 2 is 14. And notice I'm writing plus or minus because 56 could come from -1 and -56, not just +1 and +56. Let's see. 6 can't work. 5 can't work. 7. I think 7 works, guys. How many times does 7 go in? Ocho times. So let's see. The leading coefficient of this is 1, so that means Q is just like plus or minus 1. All right. So if I want a list of all possible P's over Q's, it would just be all of these over all of those in all possible combinations. All right, so that list actually isn't going to be that interesting in this case. It would just be plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 7, plus or minus 8, plus or minus 14, plus or minus 28, and plus or minus 56, right? It'd be the ones that I had. But if there was, say, like plus or minus 3 here, then I'd have to also pair up this over 3, and this over 3, and this over 3, and this over 3. I'd have to, list all possible arrangements, combinations, so to speak, of those things. So this would be all possible rational zeros, okay? All possible rational x-intercepts. And notice that there's, 16 there. That's a lot less than the infinitely many that I started with. So we narrowed our list down pretty well. So let's say if this was part A of this problem, what if part B said find them, find all roots. Find them. Well, just to help myself out here, I'm going to do a little bit of Descartes. So I'm going to do the positive, negative, imaginary chart. And let's check this out here. So for Descartes, it's always worth at least doing the positive ones for Descartes because you don't have to really do any work. So here's one change. Looks like 2 changes for positive. Do I have a concurrence from the audience? Because it went from positive to negative. That was 1 change. Negative to negative stayed the same. Negative to positive. Right, so it's the changes that I'm counting. And I'm expecting 3 total, which actually, if this is 2, I can't have an odd number of imaginaries. So this, I don't even have to do the other half of Descartes. I know that that's got to be 1. And then there's one other possible combination here. What's that going to be?
0, 1, 2. Wait, so I forgot that imaginaries can't ever be odd.
You got it, because if there's an imaginary friend, there's also an imaginary enemy.
Oh, yeah.
So let's set up our chart, okay? So I'm going to do some synthetic substitution here. I've got 1, -5, -22, 56. 1, -5, -22, -56. There we are, friends. And now I've got to start guessing. Now, this is...
Why -56?
Because that was... Oh, good catch, good catch. You got my back. You got my back. Whew. Good save. So now the things that I'm going to try here are the P's over Q's. All right, I'm going to try these things. But when combining it with Descartes, I can be even a little bit more clever. I'm going to start combining all of my skills that'll be the ultimate root finder. I'll be like some sort of dog that smells out roots. Apparently. I don't know. So here we go. Now question, should I start trying positives or negatives first?
Negatives.
Now negatives, I am certain that a negative root exists, but there's only one of them. Positives, it's possible there's none of them. And then I'd have to try all 8 positive combinations before I'd get there. Huh. Man, that's quite the dilemma. But if the positives do exist, there's twice as many of them that exist. Well, let's just do negatives. So let's start with some smaller numbers. I don't know, -1 maybe. closer to 0 numbers, I guess, is what I'm describing here. So bring down the 1, multiply is -1, -5, -6. Multiply is +6, that's going to be -16. Multiply is +16, so that's going to be what, 72, I believe. Did I do that right? I hope so. Well, I'm trying to save us some time on this synthetic substitution part. So let's try -2. Let's do that. -2. So plug in a 1. Here we go. Here we go. -2 times 1 is -2 with a -5 is a -7. +14 with a -22 is a 6 and a 2 is 8, I think. -8. And that's +16, and that's a 72. Which, the fact that there's no change in direction, these are exactly the same value, would suggest somewhere between here there is a max or min. Not that we're gathering that information right now, we're just interested in x-intercepts, but it's true nonetheless, somewhere in there. Okay, would be that. Now question, would I try this?
No.
Why? Because the rat root theorem says it's not going to be -3. Right? The next thing I should try is the 4. Let's try this. Here we go. -4, -5 is -9. Here we go, here we go. Multiply those as +36 -22. 16 minus 2, 14. Guys, what? And that's +14. Guys, no way. No way. Here we are. What?
Oh, yeah, it equals 0.
And -14 times -4 times 14 is -56. What? 0. We found one. Dun 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 dun. We found one, and we're done as far as the negatives are concerned. I don't want to look for any more negatives. I'm not going to try -7, -8, -14, -28, -56. No, because I knew that no matter which situation I was in, there was only ever going to be one of them. Okay? So I could start looking for positives, or maybe it's worth, because there's kind of a 50-50 chance here, either they're both positive or they're both imaginary.
Just do positives because the number's annoying.
Well, but better yet, I actually have a depressed polynomial here.
Oh.
G of x is equal to x squared minus 9x plus 14. And it might be worth determining whether or not that's factorable at all.
It is.
And it is. Okay.
2 and -7.
Yeah, 2 and 7. Okay, so +2, +7 are going to be the ones that work out in the end. So I could actually keep making another chart, or I could try to factor it since I've hit a quadratic. All right, once you do that, that's not a bad idea. So x squared, actually let me write this in purple. Purple, friends, x squared minus 9x plus 14 equals 0. And yeah, the factors of 14 are 1 and 14, 2 and 7. And those ones add to be 9. And of course, we'd have an x with it. Well, add to be 9. Yeah. We're good. So x with a 2, x with a 7. Their signs have to be the same because they multiply to be positive. And they add to be negative, so negative, negative. And then, of course, we'd set each of those equal to 0 and solve. You guys know all this stuff. Actually, you guys wouldn't even have to do the solve part. You just know if that's a factor, then 2 is the answer, right? We. So x equals 2, x equals 7. And what was my third one? -4 up there. So notice, what situation did I have? Was Descartes right? Yeah, I had this situation right here, where I had 2 positive and 1 negative, right? And all of my other skills apply, right? Where if I wanted to skip around a little bit, I could. If it looked like I was getting further from 0. If I saw a sign change between 2 of them, I'd be like, aha. And actually, there is sometimes this can occur. What if I knew that there was going to be a negative one? And what if I tried all of these negative ones and they didn't work? What would that tell me? 0 is not a negative, though. Correct. But Descartes doesn't actually tell us about that. In fact, anytime you don't have a constant, if there's no constant term, then 0 would be one of your roots. I could tell you that much. But if I knew there was a negative, and I tried all of my negative rat roots, and none of them worked, but what if I found like there was a sign change right here? What if this was true? What would that tell you? That there, yeah, somewhere between -1 and -2, there would have been a 0. However, I wouldn't have had any -1 or -2. I don't have any numbers between -1 and -2 from my rational possible answers. So that would have meant that there is an irrational 0 between there. So I just want to point out, this is not all of the possible real roots. This is all of the possible rational roots. So irrational ones like the square root of 3, like pi, like e, all could still exist. So just be aware of that. Okay? And also the other really devious trick sometimes that can occur, you might remember like when you have a graph and there's a ricochet, that root actually shows up twice. So it's possible you might have to sometimes like try -4 a second time, which can be really devious. So let's look at one more problem.
What's devious mean? Like sneaky?
Sneaky, yeah.
I'm picked that up.
Like a diva? I don't think that's spelled the same. So let's do another example, friends. Find all zeros. Gotta find them zeros. Here we go. What if f of x equaled 2x cubed minus 3x squared minus 9x plus 10? So first things first, let's rat root this.
That's such a gross word.
Rat root. So my p's. That's enough, friends. Plus or minus 1. Hey, friends. Guys. No cyberbullying. We're in the middle of a video.
Yeah.
Let's not annoy each other. Let's find these zeros as a team. Plus or minus 1, plus or minus 10, plus or minus 2, plus or minus 5. Those are all my p's there. How about my q's? My q's are going to be plus or minus 1, plus or minus 2. So my p's over q that I'm trying, I just want to point this out. Normally you don't have to pre-write this list anyway. I would have had 1 over 1, 2 over 1, 5 over 1, 10 over 1, right? So I'd have plus or minus 1, plus or minus 2, plus or minus 5, plus or minus 10. But then I also have to try all of these over the 2 because the q is my denominator. So I could have plus or minus 1 over 2, it's a half. Plus or minus 2 over 2, I already have that, right? What's 2 over 2? That's 1. I already had that guy. Plus or minus 5 over 2, I don't have that. And plus or minus 10 over 2 is 5, and I already had that one. So here's my list of possible rational zeros. And there will not be a rational zero that's not on this list. All right, that's the guarantee. So let's do some Descartes. Positive, negative, imaginary. How many total am I expecting?
You guys write that entire list down or not?
You don't, although sometimes on homework they'll specifically only be looking for that list, and then they'll say, we don't actually care what they are, we just want to know what they could have been.
Yeah, I just want to know because my thing is...
Yep, yeah, don't worry about it, don't worry. So, how many possible, or how many zeros does this have?
It has 3.
It has 3, guaranteed, right? Descartes, how many sign changes do I have? 1, none, 2. So there are 2 positive, and actually similar to the last situation, I know then there must have been only 1 negative. Or there could be 0, 1, and 2. Yep, I agree. So, all right, what do you guys want to try first? Negatives? Negativo. Here we go. All right, let's set up our chart. 2, -3, -9, 10.
Wait.
And in my column here, I'm going to do P's over Q's.
Let's start with
You want to start with -1?
-1.
Let's do this then. Let's do this, friends. So, I'm going to do this rapido. -1, bring down the 2. So -2, -5, +5, that's -4, +4, that's 14. So, what should I try next?
-2.
-2, it's the next one on our list. Why not? Bring down the 2. -4, -3 is -7. That's +14, and that is +5. And oh, ding, 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 ding.
So x equals -2.
X equals -2 is one of them.
And now we have
I don't think that's bad.
Should I try -5?
Can we factor?
Oh, you're checking out the depressed polynomial already?
Yeah.
For fun, even though I know we're really good at that,
But there's a 2.
let's just keep practicing with the chart for fun. It is factorable, I'll tell you that much. But I want to teach us kind of our chart analytic skills today.
Not the negatives.
Could you use a depressed polynomial?
You could. We'll do a chart with the depressed polynomial.
And we're gonna
But-
do positives.
And why are we only doing positives?
Because they're going to find negative.
Because there's only ever going to be one negative in the situation. We just found it.
It's a lot easier to find a positive than to find a imaginary.
So let's redo our chart.
1.
I'll do 2, -7, 5, and you want to start with +1, you're saying? Okay, bring down the 2. 2 times 1 is 2. Oh, what? What? No, they didn't. What?
Oh.
Man, we're on a roll.
Yeah, how did you know? Feeling I think we should do 5.
Well, let's keep going. Let's just do this in order for sake of curiosity, so we can kind of determine trends. Oh, actually, since I found another one. What did I just do?
We depressing it.
Yeah, let's depress it again.
Why are you guys so freaking mean?
So we'll have 2, -5. Wow, this is going to be quick to do this math here. So we're going to try +2. 2, 4, -1. Okay, that doesn't work. Let's try. Should I try 3?
5.
Why aren't we trying 3?
It's not ours.
Because it's not on the list. Why aren't I trying 4?
It's not ours.
Because it's not on the list. So I'm trying 5. Okay, watch 5. Bring down the 2. 2 times 5 is 10, and no. But what's up?
Zero is there.
There's a 0 between 2 and 5. Now, I can't say yet that it's irrational. Are any of my numbers up here between 2 and 5 that I should try first?
No. Oh, yes. 5
halves.
5 halves.
I got it.
5, 2. We can have 5.
Wait, why are we doing that? What just happened?
X equals. I like this a lot better.
So, we knew that a 0 occurred between here, right?
Yeah.
And the only numbers that I had between 2 and 5, I had 5 halves, which is the same as 2.5. So I tried 2.5, brought down the 2, 2 times 2.5 is 5, cancels out with a -5, and it worked out. All right, so my zeros, I had x equals, what did I have? 1, -2, and 5 halves. So according to Descartes, which situation was I in?
The first one.
The 2, 1, 0.
Yeah.
Right? 2 positive, 1 negative, no imaginary. All right? And we didn't have to use the charts the whole way. I could have actually just taken this and factored it, set it equal to 0, and it would have worked out. But I just wanted us to be chart ready. Because what if this problem didn't reduce to a quadratic right away? What if this was like a 7th degree and I had to like keep working at it, you know? So I just want to make sure you're good with those skills. So thanks for watching, internet friends. That's the idea. Rat root. Have a great day. Root root.